Good day and welcome back. Today I want to take you through an example of the basic ideal gas law and why we deal with gauge versus atmospheric pressure and why we need to deal with Kelvin. So typically this example will come up as, let's say we have some sort of gas. Let's go maybe a compressor station. We're dealing with methane. Okay, let's say we have a certain pressure of, let's say 250 kPa for pressure. Now, you guys will often measure that in a gauge. With a gauge, I mean. So let's say we have a temperature of, 10 degrees C. And let's say we have a volume of, whoops, that's not 2, that's 1. And a volume of 10 meters cubed. Okay. Now, oftentimes we want to take this into a situation of standard conditions. So sometimes they'll give us what we did over here in state 1, and they'll ask us, what is this described as in standard conditions? So standard conditions we know are 101.3 kPa, and that's in atmospheric. We don't have to worry about putting that into gauge. And our temperature at standard conditions is 15 degrees Celsius. They'll often ask us, okay, what's that volume? Sometimes you'll even see this in a rate. We'll go over that a little bit later at the end. So how many meters cubed is this gas going to be at standard temperature and conditions? You'll even see this on fuel pumps as you fuel up your car. Okay, so I just want to make sure you guys have this straight in your head. So there's two kinds of pressure basically. Two kinds of ways of describing pressure. Atmospheric. If they don't give you what it is, you by default assume it's atmospheric. So some of the units that they will put atmospheric units of pressure are kPa. So by default, if they don't tell you that it's gauge, you assume it's atmospheric. Sometimes you'll also see it as kPa, like I wrote it before there. And you have another type of pressure, or description of pressure, which is gauge. And that's what you measure. You'll always be given what this is. So you'll be given kPa, a G you'll often see. You'll also see, like I wrote it up there, gauge. So just know that this is the default, atmospheric, unless they tell you that it's gauge. So I guess we can also conclude that you guys know now that pressure, how do these relate? P atmospheric plus P gauge. I.e., if you're given a gauge, you just simply add 101.3 to it to get the real pressure that we need to deal with in our ideal gas equations. So why don't we just all make all our gauges read in atmospheric? Well, it's just a simple, it's easier to build a gauge that reads not relative to 0 atmospheres. So basically, if you build, that's the way old gauges were built. Well, that's the way they're built now today as well. If you built a gauge that read atmospheric, you basically have a gauge plus a barometer on it. So it'd be a really sensitive instrument to build and a really expensive instrument to build. So its physical practicalities is why we have to use this equation. Because one that measures both of them is just too damn expensive to build. And they don't last. They get beat up. Even our gauge ones get beat up. So why do we work in Kelvin versus Celsius? Well, we need to make sure that we're using datums of 0, meaning we can't have negatives in these equations. So are we going to work in conditions that are below 0 degrees Celsius? Hell yeah. Are we going to work in situations below 0 Kelvin? No, 0 Kelvin where atoms don't move. We wouldn't be living. I think it's something crazy like minus 459 degrees Fahrenheit. So we know we're not going to have a negative if we work in Kelvin. And negatives will give us wonky answers in these equations. Okay, so back to our question here. We basically have two states going on. So I think you guys understand this stuff now. We have two states going on. We have the state previously, and we have the state of standard conditions later on. Okay, so let's just take ourselves through this. We know our P1, our ideal gas law. So oftentimes in these equations, why do we know it's ideal gas law? Well, they give us an R. So as soon as you're given an R, you basically know you're dealing with an ideal gas. 0. What is it for methane? 518 kilojoules per kilogram Kelvin. Okay. So P1 V1 equals the mass. Note here too that something you have to understand is that mass doesn't change. Okay? So we can heat this gas, we can expand it, we can compress it, we can do all we want to it. We can heat it up, we can cool it down, but the mass will not change. The volume will change, the temperature changes, pressure changes, but the mass will never change. Okay? And then, let me get this straightened out. Over here we have P2V2 equals the mass, the gas constant, times the T2. So we know this, we don't know this. We don't know this. We don't know this, but these two are constant to both, okay? And we know the temperature too, yeah. Okay, what do we know over here? We know this, we know this. We know those two are constant, and we know this. So what can we do here? We pretty much know it all for this equation, so we can play a little trick here. Let's take out the constants. If we take out the constants, we're given P1, V1, divided by T1 equals our constant, m times the r. Well, we can do that on the other side too and equate them. P2V2 equals T2, or divided by T2, right? Do you guys understand? So basically we divided both sides of this equation by T1. So we're given P1 V1 over T1 equals this constant. Did the same thing over here, and then we just equate them because they're equivalent to both. Just a nice way of getting us down to one equation. Now we don't have to find that m. So what are we after here? We're after this second volume. Okay, nice little symbol here for drawing this equation over here. So let's solve for V2. If you guys don't understand how I manipulate these equations, just give me a shout in the comments, but I've done it so much, it's pretty simple to me. If it's not for you guys, give me a shout and I'll go through it in more detail later or in future episodes. So basically what I'm going to do is divide both sides by P2 and multiply both sides by T2. That basically just gives me, singles out my V2. So, and now I need to multiply both sides by T. I made a boo-boo here. Hopefully somebody caught that. Just taking this over here and putting it over here. Here we go, multiply both sides by T2 and divide both sides by P2. Okay, let's work through this. So P1 is what? 250 kPa. Gauge. Okay, to convert that, we know we got to add 101.3 kPa times our volume. What's our volume? 10 cubes. I always put my units, otherwise I screw up. I'm going to run out of room here, so pay attention. Our temperature 2 is 15 degrees C plus 273. This whole thing divided by T1, which is 10 degrees C plus 273 Kelvin. Now, P2 is 101.3 kPa. That's already in atmospheric. All right, I'll grab my handy dandy calculator here. Again, if you guys want me to go through these calculations in more detail, no problem. Just let me know in the comments. So going 250, 101.3, add that, 10 cubes times 15, 273 plus times 10, 273, add 101.3 times divide. Okay, that gives me, where's my spot here? That gives me 30, garbage. 35.3 meters cubed. Okay. Let's check this to make sure it's real. Okay, this is one thing I always like to do. Especially with a gas, because it's easy to figure this out. Oops. Okay, so we took this gas and we decreased the pressure and we increased the temperature. Okay, so I know on a gas, if I decrease the pressure, my volume should expand, and I heated it up a bit, I should expand more. Pressure will have a bigger effect, but anyways, so I should be expanding. My original volume was 10 cubes, I'm 35 cubes now. Okay, this answer makes sense. That's cool. Another application to all this is a compressor. So when you're given a compressor rate of, let's say, 30 SCM per day, 30 cubes, that's standard cubes per day. You can also, that's always given in standard temperature and standard conditions. Now, you also know that that discharge pressure might be 250 kPa and a different temperature. It might be really hot because it hasn't gone through the coolers yet. So if you want to actually calculate that volume, you just apply what we did here backwards in a different way. So your state 1 and state 2 will just change, and then you can get the actual volume of that volume rate of that gas going through. I hope that makes sense to you all. If you want me to go through a compressor calculation to kind of take it in and out of standard conditions, no problem. Just give me a shout. Take care, gentlemen and gentettes.